Yeah, so from this we get the mass density of collagen, and with the mass density of collagen and this water to organic mass ratio, we get the tissue volume. This was the left-hand side of our equation we wanted to check based on experimental values, because mass density of water we know, mass density of collagen, okay, this is 1.4, and R is tissue specific. This is measured from tissue to tissue. Okay, and that's how to check on a couple of different tendons. This is here rat tail tendon and kangaroo tail tendon. These are the people who gave the correct data. There are between 1953, 1991, 1973, 3 different protocols and so on and so forth. So no cheating possible, and that's the result. So it's an R-square far beyond 95%. So it's interesting. It definitely means the extrafibular space grows proportional to the let's say gain in fibular volume. Okay, and it grows almost with beta 1/2. For 8, so it might be 5, I don't know. So it's per 1 piece fibril which you gain half a piece extrafibular volume. And then you can do all beautiful computations, right, in half a second on the MATLAB. As a function of water organic ratio, you can now say the volume fractions, extrafibular, fibular. First you have to saturate the pores from the 12%. Then if the 12% are saturated, then the fibrils, so it's like this basically. From here it is, here it is totally dry. So with 0 it's absolutely dry. It's totally fold together. The entire tissue is a fibril, everything is yellow, fibrils are yellow. And then the green part, this is how the extrafibular space evolves. Here is our rule which we identified, and then the fibrils, if the fibrils are saturated, they stay constant. They cannot go, the molecules cannot go further apart than 1.1 or 1.2 nanometers, and just then the extrafibular space is growing. Okay? In the same sense, we can show here how the tissue is swelling. Right? Here it's 1 is the totally dry tissue, and then it swells up to 3 times of its original size. And then you can also say how the fibril is composed, right? With the collagen, the water, and the air. Okay, and we are fairly sure that, and you will see in 10 minutes, that this is absolutely valid for any collagenous tissue. We use it afterwards for all these different bones, and it works very well. So now we have this unmineralized tissue, and now the last question is, okay, now how to put mineral there, right? So the idea would be now in bone that you start with this, and then the mineral starts to precipitate. So in the fluid part here, there is now a solution with the ions, and then the ions precipitate. And this is now very new work which we are in the process of submitting. I don't know whether my postdoc already submitted it. We decided to resubmit whether I'm here, so but I didn't check my email. So this is the first time I present this. So now we want to model, or we modeled it, the bone tissue evolution during mineralization. So the proposition is the following. Again, very primitive. Let's assume these tissues and the fibrils, the extrafibular space, and the entire extracellular tissues, they are closed thermodynamic systems. So the water during the mineralization, no water in, no water out, during this couple of hours or weeks it takes then, it's fully thermodynamically closed. And the only thing which can be happen is that we have a phase transformation ionic solution with about 1 gram per cubic centimeter into solid hydroxide with 3 gram. And let's write down for this system the system-specific mass conservation rule, which becomes fairly simple. I don't give the equations. And then combine this idea with rules 1, 2, 3 I've shown before. Where is the mineral? How is the tissue before it mineralizes? And what's the relation between mineral and collagen if it's ready, if the tissue is fully mineralized? And then check again. And now check with Newton diffraction, because the X-rays, they are hard to get through the mineralized tissues, so Newtons are better. And the fibular volume changes can be measured, and we can check this fibular volume change. Okay? And now, very fast, the experimental validation is really, again, astonishing, right? We have wet tissues, dry tissues, partially dehydrated tissues, and again, it's different bones, different laboratories, and so on and so forth. And it's built on all the other 3 rules I've shown before. Okay, and then we can plot nice things, right? Like the diffraction spacing. so the difference between the collagen molecules, as a function of the final mass density at different desiccation degrees. So the more it dries, let's say if we have a dry tissue, then the fibrils, they get bigger and bigger with increasing mineral content. If you have a wet tissue, then the fibrils get smaller and smaller with mineral content. Was a big paradox in structural biology. Now it's hopefully the result of just a closed thermodynamic system. And again, we can do as a function of mineralization degree, the volume fractions of the system. And with this, I stop now the structural biology part, right? So we are in the situation that we think that we can say something quantitative about a collagenous tissue, be it unmineralized or mineralized. And I'm relatively optimistic that at least parts of this can be transferred to soft tissues and also to the cardiovascular regime, probably. And now let's do some mechanics on it, right? So because what we started earlier is to identify now all these minerals, the collagenous waters, how they would build up the mechanics of the tissue. And now very brief, what we use is continuum micromechanics, so it's a continuum approach, but a multi-scale continuum approach, so we have stresses and strain and stiffnesses, and we don't know the stiffnesses because they depend on the microstructure, so we represent a simplified but complex enough representation of our material, which consists of such a volume, which is subjected to homogeneous strains. The volume must be smaller than the structure and must be larger than the inhomogeneities, and all the microstructures are represented in terms of what is called phases, which a little bit comes from chemistry, so they are more or less chemically pure. So you tell me when I have to stop. 1 minute, I'm already over. No, it's okay. It's still okay? Okay. And they have mechanical properties, these phases, like elasticity, strength, viscoelasticity. They have a shape and they have volume fractions. And then the interesting thing is that that if this is a kinematically compatible continuum, also this volume, then the strains, the microstrains, the average over the microstrains in these volumes, the volume average of this is identical to the homogeneous strains put at the boundary. So it's a result of the strain compatibility. It means that this volume stays a volume, no cracks, no disintegration. So that's strain averaging, that's the first important thing. Second thing is stress averaging. If the traction forces at the boundary, all related to a macroscopic stress, are in equilibrium with the stresses inside, then the microstresses, average over the microstresses are the macrostresses. And then we need some idea about the fields inside this volume element, and these fields are approximated on the basis of so-called matrix inclusion problems. I don't go into detail. It's not a matrix inclusion problem. It's always the question, you know, a matrix inclusion problem is too easy. It's correct, but you use the matrix inclusion problems as mathematical entities, like you would use finite elements for the entire structure. So you use different such matrix inclusion problems together as to fulfill, and now it's important, precisely the stress and strain average rule. And then you get this well-known formula where you have the stiffness of such a piece of material as a function of the stiffnesses of the faces and of the volume fraction and of the shape. And this we apply to our bones, but we have to be a little bit more careful. We need more than one. So this is kind of material at 1 millimeter. Here we would not find constant properties. So we make out of one phase another structure, right? So we again here see the course with the cells swimming, here the lacuna cells, and then here again, here is our extracellular material. We are back, what I was discussing all the time. How much fibrils are there, how much mineral, how much collagen is all now in here. Is the fibril at the extratubular scale, and then it's here the mineral in the extratubular scale, and finally the fibrils which some mineral into them, and the collagen itself with another process. And now what we identified over the years is to say, okay, now it's the big hope, which has been really fulfilled, the hope, that if we know the mechanical properties of this molecular collagen, the mechanical properties of the minerals, and the mechanical properties of the water, then based on all the rules I've shown before, I should be able to predict the mechanical properties of bone in a general sense. Okay, and that again we have to test. The best way to test elasticity for this type of materials is ultrasound tests. First of all, because you have a lot of in literature. Secondly, because you don't have the problem with elastic and elastoplasticity because the amplitude is very small. So really compute, you get elasticity. So the idea is you have here some acoustic signal with some frequencies. Some frequency, you measure the velocity of the acoustic signal from here to here. From the velocity and the transition time here, you get the wavelengths, and now it becomes interesting. You again think in terms of an engineer or mechanician. If you have a wavelength like this, it means you have here a high stress, a low stress, a low stress, for example. So it's a structural test, and the material which you test is smaller than the structure. So the material is like this, because the material has to feel a homogeneous boundary. Huh? So the material you test with a wavelength of some length is the material which is 1 order of magnitude, practically speaking factor 5, 6, smaller than the wavelength. You don't test the material at the size of the wavelength, but at a smaller size. But still, if you change the wavelength, then you can characterize the material at different scales non-destructively, as long as the waves go more or less straight through the material. Once you have big deviations, then it's not anymore correct. But this we use extensively, so we have different frequencies, and the different frequencies we send to the materials in different directions, and then we get more or less the full elasticity tensor with the correct mass densities and so on. Okay, so we need the properties of the mineral and of the collagen, and then we test, we put the volume fractions, so let's say the stiffnesses for mineral and collagen are the same for each and every bond. And then we have to confront it with a lot of different bonds. A lot of different bonds means we need all these volume fractions. For example, we can take all the rules from before. We know the mass densities, and from the rules we derive all these different volume fractions. Or we take it directly from experiments, a little bit historically, because this model was older, so we did it first directly. And now with the rules it's even simpler. So we put a lot of different volume fractions into one and the same model. The model gives us a lot of different elasticities. And then all this lot of different elasticities have to be tested by a lot of different tests at different frequencies, delivering us the stiffness of this material, small, larger, larger. Right? And to give a glimpse on this, back to these universal properties, hydroxyapatite from ultrasonic tests. It is confirmed meanwhile by molecular dynamics, so this is cast in stone. Molecular collagen, we have to be careful. We are introducing molecular collagen as the elementary building block, not collagen with water and so on. It's just the molecules. So you have to take something where you have no water and just the molecules. So if you take, for example, dry tail tendon, which is the one you can find in literature, you get relatively high Young's moduli, and they are consistent with molecular dynamic simulations and so on. But this is what is molecular collagen about. What you have in the literature is very often a composite between collagen and water, or a lot of water, and then it goes down orders of magnitude. But this would be a higher step of the model, so attention. I'm not talking about wet collagen, then collagen, whatever. It's collagen. Okay, and water. And these are these rules from before, and if you put it there, this is at this scale. Almost a perfect prediction. There's no fitting, zero fitting. If the points are on the curve, it's good. If not, it's not good. And this is at this scale, and we did a lot of different other things. And before I stop with this, we went one step further. This was elasticity. Now, if you go to elastoplasticity, we say, okay, the crystals are glued together. There's water in between. Once we have a certain limit surpassed, then they start to glide on each other. And they glide, the more the crystals glide, the more load comes to the collagen, and the collagen would fail as a Rankine criterion, so brittle. Collagen, there is no chance for plasticity. Material speaking, a lot of people say, well, it's ductile and so on, but it's a consolidation problem. You have the water, you press out the water, but it has nothing to do with collagen strength. If you take a piece of collagen fiber, you make a direct strength test, you find a lot of papers on that. It goes up and then it's suddenly over. So we have a plastic mineral water system with a brittle collagen reinforcement. It's very close to reinforced concrete. Okay? And then we have to do a lot of theory, which I don't give. The relation between, here it's really heavy computing, between the strains in the phases and the macroscopic strains. And what you're basically doing is we are trying to transform all this big tradition of return mapping algorithm and consistent, all this old 1980s, 1990s finite element technology into the world of continuum macromechanics, which is very much analytically driven. So we use, so to speak, the analytical formula as the structural background, and feed it with return mapping algorithms. And this is a lot of work you can ask. You can ask my colleague, who is an expert on this. So now, and this is one of the validations again. Unilateral strength, you know, for different tissues works very well. This is now the independent strengths. Independent strength checking. In tension, it's less than in compression. That's very logical, right? In tension, it would fail. This needle would fail. This kind of crystals, right? And in compression, you have to press much longer until this needle would fail in tension. If there would be no collagen, it would be 1 to 10, like in sandstone or concrete and so on. Since there's the collagen, which is acting the same in tension and compression, because it's, you know, because it's fixed by the mineral. The collagen is really working like a column, not like a rope. It cannot buckle, no chance. Okay, that's the mechanical reason for this. So that would leave us to, again, some kind of universal mechanical design of bone tissues governed by plastic sliding events between mineral crystals before collagen fibers break, which is consistent with the experimental evidence. So here I could more or less come to an end.
You have 5 minutes.
Okay, then I take 5 minutes to come to an end. It's no problem. It's very flexible. Okay, so what I basically want to say is we have identified a few rules for collagenous tissues, so to speak, mathematics-based or computer-aided structural biology. This is how I would call it. And we can use it in order to make multiscale